In the vast expanse of space, 1.5 million kilometers from our home planet, a remarkable instrument floats in perfect stillness. The James Webb Space Telescope, humanity's most sophisticated eye on the universe, maintains its eternal vigil among the stars. Its golden mirrors, arranged in a hexagonal pattern like the compound eye of some cosmic insect, capture light that has traveled across unimaginable distances and epochs of time. This telescope represents the culmination of decades of human ingenuity and collaboration. Scientists and engineers from around the world poured their knowledge and dreams into its creation, designing each component with meticulous precision. The result is an observatory capable of peering deeper into space and further back in time than any instrument that came before it. Every photon that strikes its mirrors carries with it the secrets of distant worlds, ancient galaxies, and the fundamental processes that govern our universe. Webb's primary mirror spans 6.5 meters across, composed of 18 individual segments that work in perfect harmony. Each segment is coated with a thin layer of gold, chosen not for its beauty, but for its exceptional ability to reflect infrared light. This golden surface gives the telescope its distinctive appearance and enables it to see through cosmic dust clouds that would blind other instruments. The telescope operates at temperatures colder than the depths of space itself, cooled to just above absolute zero to prevent its own heat from interfering with the delicate observations it makes. The location of this extraordinary instrument is no accident. Webb resides at what astronomers call the second Lagrange point, a gravitational balance point where the combined pull of Earth and the Sun creates a stable environment. Here, the telescope can maintain its position with minimal fuel consumption while keeping its back turned to both our planet and our star. This positioning is crucial as it allows Webb's instruments to remain in perpetual shadow, shielded from the heat and light that would overwhelm its sensitive detectors. From this vantage point, Webb surveys the cosmos with unprecedented clarity. Its instruments can detect the faintest traces of light from objects so distant that their illumination began its journey when the universe was young. The telescope's 4 primary instruments work together like a symphony orchestra, each contributing its unique voice to our understanding of the celestial realm. The near-infrared camera captures detailed images of cosmic phenomena, while the near-infrared spectrograph breaks down light into its component colors, revealing the chemical composition of distant objects. The mid-infrared instrument peers through dust clouds to observe the birth of stars and planets, and the fine guidance sensor ensures that the telescope maintains perfect pointing accuracy throughout its observations. The mission that brought Webb into existence began decades before its launch. Scientists recognized that to truly understand the universe and our place within it, they needed an instrument capable of observing in infrared wavelengths. Unlike visible light, infrared radiation can penetrate the dust clouds that obscure much of the cosmos, allowing astronomers to witness events and objects previously hidden from view. This capability is particularly important when studying the formation of planetary systems and the potential for life beyond Earth. The development of Webb required innovations in multiple fields of technology. Engineers had to create mirrors that could unfold in space with extraordinary precision, design heat shields that could protect delicate instruments from solar radiation, and develop cryogenic cooling systems that could operate reliably for years in the harsh environment of space. Each challenge required novel solutions, pushing the boundaries of what was thought possible. The telescope's journey to its current position was itself a marvel of engineering and navigation. Folded like origami for its launch aboard an Ariane 5 rocket, Webb underwent a complex deployment process that unfolded over several weeks. Each step of this process had to work perfectly, as there was no possibility of physical repair once the telescope reached its destination. Mission controllers watched with careful attention as solar panels deployed, heat shields unfurled, and mirrors aligned themselves with microscopic precision. Once operational, Webb began to revolutionize our understanding of the universe. Its first images revealed cosmic phenomena with clarity that surpassed even the most optimistic expectations. Distant galaxies appeared as never before seen, their spiral arms and stellar nurseries displayed in exquisite detail. Nebulae glowed with colors that told stories of stellar birth and death. The telescope confirmed the existence of some of the most distant galaxies ever observed, their light stretched to infrared wavelengths by the expansion of the universe itself. Yet perhaps the most profound discoveries lay not in the realm of distant galaxies, but much closer to home, in the study of worlds orbiting other stars. For it is here that Webb would make a discovery that would capture the imagination of scientists and the public alike, a finding that would challenge our understanding of life's place in the cosmic order. The concept of planets orbiting stars other than our Sun was once purely theoretical. For most of human history, our solar system represented the only known example of worlds circling a stellar companion. The existence of what astronomers call exoplanets remained a matter of speculation and hope rather than scientific fact. This changed dramatically in the 1990s when the first definitive detections of planets around other stars began to emerge. These early discoveries revealed worlds unlike anything in our solar system, giant planets orbiting so close to their stars that their surfaces would be molten rock and metal. Worlds with eccentric orbits that would take them from scorching heat to freezing cold and back again. Planets larger than Jupiter but less dense than Cork, their atmospheres puffed up by the intense radiation of their nearby stars. Each new discovery expanded our conception of what planetary systems could look like and challenged our assumptions about the processes that govern planetary formation and evolution. As detection techniques improved and space-based observatories like Kepler began systematic surveys of nearby stars, the tally of known exoplanets grew exponentially. Thousands of worlds revealed themselves, each with its own unique characteristics and orbital parameters. Some were scorching hot, others frozen in perpetual winter. Some were massive gas giants, others were rocky worlds smaller than Mercury. The diversity of these planetary systems demonstrated that our solar system, far from being typical, represented just one possible outcome among countless variations. Among this vast menagerie of alien worlds, astronomers began to identify planets that occupied a special category. These were worlds that orbited within what scientists call the habitable zone, that delicate orbital region around a star where temperatures would allow liquid water to exist on the planet's surface. The habitable zone is neither too hot nor too cold, but exists in a balanced state that astronomers sometimes refer to as the Goldilocks zone, borrowing from the fairy tale about conditions that are just right. The boundaries of this habitable zone depend on several factors, most importantly the luminosity of the host star. Massive, bright stars have habitable zones that extend much farther from the stellar surface than those of smaller, dimmer stars. A star like our Sun creates a habitable zone that encompasses the orbits of Venus, Earth, and Mars, though Venus has succumbed to a runaway greenhouse effect that makes its surface hotter than an oven, while Mars has lost most of its atmosphere and exists in a perpetual deep freeze. Understanding the habitable zone requires more than simply calculating distances and temperatures. The concept assumes that liquid water is essential for life as we know it, a reasonable assumption given water's unique properties and its central role in all terrestrial biology. Water serves as a solvent for biochemical reactions, a medium for nutrient transport, and a moderator of temperature changes. Its ability to exist as a solid, liquid, and gas at the temperatures found on planetary surfaces makes it an ideal substance for supporting complex chemistry. Yet the mere presence of liquid water does not guarantee habitability. A planet must also retain an atmosphere capable of maintaining stable surface conditions over geological timescales. This atmosphere must be thick enough to prevent water from boiling away into space, but not so thick that it traps heat and creates a runaway greenhouse effect. The delicate balance required for long-term habitability involves complex interactions between a planet's size, composition, magnetic field, and orbital characteristics. The search for potentially habitable exoplanets has revealed several promising candidates over the years. Planets like Kepler 452b, often called Earth's cousin, orbit sun-like stars at distances that would allow liquid water to exist. Proxima Centauri b, the closest known exoplanet to Earth, circles a red dwarf star within its habitable zone, though questions remain about whether such worlds can maintain atmospheres in the face of intense gas T. Stellar radiation. Each discovery has added to our understanding of the conditions that might support life beyond our solar system. As these discoveries accumulated, astronomers realized that they needed more than just the detection of potentially habitable worlds. They needed to study the atmospheres of these distant planets to determine whether they actually possessed the conditions necessary for life. This is where the James Webb Space Telescope would prove invaluable, as its unprecedented sensitivity and infrared capabilities would allow scientists to analyze the chemical composition of exoplanet atmospheres in ways that had never before been possible. The technique that enables this remarkable capability is called transit spectroscopy. When a planet passes in front of its host star as seen from Earth, it blocks a tiny fraction of the star's light. During these transit events, some of the starlight passes through the planet's atmosphere before continuing on its journey to our solar system. As this light travels through the alien atmosphere, it interacts with molecules present in the air, with different chemical compounds absorbing specific wavelengths of light. By analyzing the spectrum of this filtered starlight, astronomers can identify the signatures of various atmospheric components. Water vapor absorbs light at particular infrared wavelengths, as do carbon dioxide, methane, oxygen, and countless other molecules. Each compound leaves its own unique fingerprint in the spectrum, allowing scientists to determine not only what chemicals are present in a distant atmosphere, but also their relative abundances. This process requires extraordinary precision and sensitivity. The signals that astronomers seek are incredibly subtle, representing changes in stellar brightness of just a few parts per million. Detecting these minute variations requires instruments capable of measuring light with unprecedented stability and accuracy. The James Webb Space Telescope's design makes it ideally suited for this challenging work, with detectors sensitive enough to pick up the faintest atmospheric signatures from worlds many light-years away. The analysis of exoplanet atmospheres has already yielded remarkable insights. Webb has detected water vapor in the atmospheres of several distant worlds, confirmed the presence of clouds and hazes in alien skies, and measured temperature variations across planetary surfaces. Each observation adds to our growing understanding of how planetary atmospheres form and evolve, and what conditions might be necessary to support life. It was during one such observation campaign the Webb made a discovery that would capture headlines around the world and spark intense debate among scientists. The target was a planet designated K218b, a world orbiting a red dwarf star some 120 light-years from Earth. This planet had been known to astronomers for several years, identified as a potentially habitable world orbiting within its star's habitable zone. But it was Webb's detailed analysis of its atmosphere that would transform this world from just another exoplanet into what some scientists would describe as having a 99% chance of hosting life. K218b represents a class of planets that has no analogue in our solar system. With a mass approximately 8 times that of Earth and a radius about 2.5 times larger, it falls into a category that astronomers call sub-Neptunes. These worlds are too large to be considered terrestrial planets like Earth or Mars, but too small to be gas giants like Neptune or Uranus. They represent perhaps the most common type of planet in our galaxy, yet their properties remain poorly understood because we have no examples in our own solar system to study directly. The planet's orbit around its host star takes just 33 Earth days to complete, placing it much closer to its star than Earth is to the Sun. However, because K218 is a red dwarf star with a much lower luminosity than our Sun, this close orbit places the planet squarely within the habitable zone where liquid water could exist. Red dwarf stars are the most common type of star in our galaxy, comprising about 3/4 of all stellar objects. They burn their nuclear fuel so slowly that they can remain stable for trillions of years, far longer than the current age of the universe. This longevity has important implications for the potential development of life. While more massive stars like our Sun will eventually exhaust their nuclear fuel and expand into red giants that would sterilize any nearby planets, red dwarf stars can maintain stable conditions for essentially the entire future history of the universe. This gives any potential life around such stars an almost incomprehensible amount of time to evolve and develop. However, red dwarf stars also present unique challenges for potentially habitable planets. These stars are known for producing powerful flares that can strip away planetary atmospheres over time. They also emit most of their energy in the infrared portion of the spectrum, which could have implications for photosynthesis and other biological processes that depend on stellar energy. The close proximity required for a planet to orbit within the habitable zone of a red dwarf also raises the possibility of tidal locking, where the same hemisphere of the planet always faces the star, creating extreme temperature differences between the day and night sides. Despite these challenges, K218b showed promise as a potentially habitable world. Its size suggested that it might possess a substantial atmosphere capable of moderating surface temperatures and protecting against harmful stellar radiation. Its location within the habitable zone meant that liquid water could theoretically exist on its surface, assuming the right atmospheric conditions were present. When Webb turned its powerful instruments toward K218b, the results exceeded even the most optimistic expectations. The telescope's analysis revealed clear signatures of water vapor in the planet's atmosphere, confirming that this essential ingredient for life was indeed present. But water vapor alone, while significant, was not the most remarkable discovery. The spectrum also showed evidence of carbon dioxide and methane, two gases that, when found together in the presence of water vapor, could indicate biological processes. The detection of methane was particularly intriguing to scientists. On Earth, methane is produced both by geological processes and biological activity. However, methane is a relatively unstable molecule that breaks down quickly when exposed to ultraviolet radiation and chemical reactions in planetary atmospheres. For methane to persist in detectable quantities, it must be continuously replenished by some ongoing process. In Earth's atmosphere, the vast majority of methane comes from biological sources. Bacteria living in oxygen-poor environments produce methane as a byproduct of their metabolism. These microorganisms thrive in wetlands, in the digestive systems of animals, in rice paddies, and in countless other ecological niches where organic matter decomposes without access to oxygen. The methane they produce eventually finds its way into the atmosphere, where it can be detected by sensitive instruments. The simultaneous presence of water vapor, carbon dioxide, and methane in K2-18b's atmosphere created what astrobiologists call a potential biosignature. While each of these gases can be produced by non-biological processes, their combination in specific proportions could indicate the presence of living organisms. This possibility led some scientists to suggest that K2-18b had a very high probability of hosting life, with estimates ranging as high as 99%. However, the interpretation of these atmospheric signals requires careful consideration of alternative explanations. Methane can be produced by geological processes such as serpentinization, where water reacts with certain types of rocks to produce hydrogen gas, which can then combine with carbon compounds to form IN, methane. Volcanic activity can also release methane from deep within a planet's interior. Impact events from asteroids or comets could deliver methane-rich materials to a planet's surface, where they might outgas into the atmosphere. The carbon dioxide detected in K2-18b's atmosphere is less ambiguous in its origins. This gas is produced by a wide variety of processes, both biological and non-biological. On Earth, carbon dioxide enters the atmosphere through volcanic outgassing, the weathering of rocks, the respiration of living organisms, and human industrial activities. The presence of carbon dioxide in K2-18b's atmosphere indicates active geological processes and possibly a carbon cycle that could help regulate the planet's climate. The water vapor signature was perhaps the most important detection of all. Water is essential for life as we know it, serving as the solvent in which biochemical reactions occur. The presence of water vapor in K2-18b's atmosphere suggests that the planet possesses substantial water reserves, though whether this water exists primarily as vapor, liquid, or ice depends on the specific temperature and pressure conditions throughout the atmosphere and at the surface. The question of K2-18b's surface conditions remains one of the most important unknowns in assessing its habitability potential. With a mass 8 times greater than Earth's, the planet's surface gravity would be significantly stronger than what we experience on our home world. This increased gravity could have important implications for atmospheric retention, ocean dynamics, and the potential evolution of life. Stronger gravity would help the planet hold on to its atmosphere over geological timescales, preventing the gradual loss of water and other volatile compounds to space. However, the planet's substantial size also raises questions about its interior composition and structure. Sub-Neptune planets like K2-18b might possess thick hydrogen atmospheres that extend deep into their interiors, creating crushing pressures that could preclude the existence of a solid surface where life might originate. Alternatively, these worlds might have rocky cores surrounded by deep oceans and thick atmospheres, creating what scientists call water worlds or ocean planets. The concept of ocean worlds has gained considerable attention in recent years, as astronomers have discovered that several moons in our own solar system, including Europa, Enceladus, and Titan, appear to harbor subsurface oceans beneath their icy crusts. These hidden seas could potentially provide habitable environments even in locations far from their parent star's habitable zone. If K2-18b is indeed an ocean world, its vast water reserves could provide ample opportunities for life to emerge and evolve. The potential for K218b to host life has sparked intense debate among scientists and captured the imagination of the public. The 99% probability estimate, while attention-grabbing, represents just one interpretation of the available data based on specific assumptions about atmospheric chemistry and planetary cars. Evolution. Other scientists have been more cautious in their assessments, noting that many non-biological processes could potentially explain the observed atmospheric composition. The debate highlights the fundamental challenge of astrobiology, determining whether observed phenomena indicate the presence of life or result from purely chemical and physical processes. This challenge becomes even more complex when studying worlds that are vastly different from Earth and subject to environmental conditions that have no terrestrial analogue. The sub-Neptune class of planets, which includes K218b, represents entirely new territory for our understanding of planetary science and habitability. Even if life does exist on K218b, it would likely be very different from the complex multicellular organisms that dominate Earth's biosphere today. The high probability estimates primarily refer to the potential for microbial life, single-celled organisms that could metabolize the chemical resources available in the planet's atmosphere and oceans. Such life forms might be similar to the extremophile bacteria found in some of Earth's most challenging environments. Organisms that thrive in conditions of high temperature, pressure, acidity, or salinity that would be lethal to most other forms of life. The search for microbial life on distant worlds requires a fundamental shift in perspective from the science fiction scenarios that often dominate popular discussions of extraterrestrial life. Rather than seeking evidence of technological civilizations or complex ecosystems, astrobiologists focus on the chemical signatures that might indicate basic metabolic processes. The detection of such signatures would represent one of the most profound discoveries in the history of science, confirming that life is not unique to Earth, but potentially common throughout the universe. The implications of discovering life on K218b would extend far beyond the scientific community. Such a discovery would fundamentally alter our understanding of our place in the cosmos and raise profound questions about the nature and prevalence of life throughout the universe. If life could emerge and persist on a world so different from Earth, it would suggest that the range of potentially habitable environments is far broader than previously imagined. The study of K218b also demonstrates the remarkable capabilities of the James Webb Space Telescope and the rapid pace of progress in exoplanet science. Just a few decades ago, the detection of any planet orbiting another star was headline news. Today, astronomers can analyze the atmospheric composition of these distant worlds and search for signs of life across the galaxy. This technological revolution has transformed astrobiology from a largely theoretical field into an observational science with the potential to answer one of humanity's most profound questions. Are we alone in the universe? As Webb continues its observations of K218b and other potentially habitable exoplanets, scientists are working to refine their understanding of atmospheric chemistry and the processes that could produce the PASTI, observed signatures. Future observations will seek to detect additional gases that might provide more definitive evidence of biological activity. Oxygen, for example, is highly reactive and would not persist in a planetary atmosphere without continuous replenishment, making it a particularly strong potential biosignature when found in combination with capillary. Water vapor. The search for life beyond Earth also benefits from our growing understanding of life's diversity and resilience on our own planet. The discovery of extremophile organisms in environments previously thought to be uninhabitable has expanded our conception of the conditions that might support life. From bacteria living in the highly acidic waters of volcanic hot springs to microorganisms thriving in the crushing depths of ocean trenches, life on Earth has demonstrated a remarkable ability to adapt to extreme conditions. These discoveries have important implications for assessing the habitability potential of exoplanets like K218b. If life can persist in Earth's most extreme environments, it might also find ways to survive and thrive on worlds that are superficially very different from our own. The sub-Neptune environment of K218b, with its thick atmosphere and potentially vast oceans, might provide numerous ecological niches where life could establish itself. The study of extremophile organisms has also provided insights into the chemical signatures that life might produce in different environments. Some bacteria produce distinctive ratios of isotopes that could be detectable in planetary atmospheres. Others generate unique molecular compounds that would be difficult to explain through purely geological processes. As our understanding of these biosignatures improves, astronomers will be better equipped to interpret the atmospheric spectra obtained from distant worlds. The technology that enables these observations continues to advance at a rapid pace. While Webb represents a revolutionary leap in our ability to study exoplanet atmospheres, future space telescopes will possess even greater capabilities. Proposed missions like the Habitable Exoplanet Observatory and the Large UV/Optical/IR Surveyor would be specifically designed to search for signs of life on potentially habitable worlds. These next-generation instruments would be capable of detecting a wider range of atmospheric gases and making more precise measurements of their abundances. Ground-based telescopes are also contributing to the search for life beyond Earth. The extremely large telescopes currently under construction will possess mirrors with diameters of 25 to 40 meters, dwarfing even the largest telescopes in operation today. These giants will be capable of directly imaging exoplanets and analyzing their atmospheres with unprecedented detail. The combination of space-based and ground-based observations will provide multiple independent methods for confirming the presence of life on distant worlds. The discovery potential of K218b has also highlighted the importance of follow-up observations and independent confirmation of scientific results. The initial detection of potential biosignatures in the planet's atmosphere has prompted additional observation campaigns using different instruments and techniques. This process of verification and validation is essential for building confidence in such extraordinary claims. The scientific community has learned from past experiences where initial detections of potential biosignatures were later explained by non-biological processes. The reported detection of phosphine in Venus's atmosphere, for example, generated significant excitement as a possible sign of life before subsequent observations and reanalysis suggested that the signal might have been caused by instrumental artifacts or misidentified chemical compounds. Such experiences underscore the importance of maintaining scientific skepticism while remaining open to the possibility of profound discoveries. The study of K218b and similar worlds also raises important questions about the definition of habitability itself. Traditional concepts of habitability have been based largely on Earth-like conditions, with liquid water on a rocky surface under a thin atmosphere. However, the diversity of exoplanets discovered in recent years has challenged astronomers to think more broadly about the environments that might support life. Ocean worlds, which may be common among sub-Neptune planets, represent an entirely different class of potentially habitable environment. These worlds might never have exposed land surfaces, instead possessing deep global oceans beneath thick atmospheres. Life in such environments would face different challenges and opportunities than terrestrial organisms, potentially leading to entirely novel forms of biology and ecology. The atmospheric conditions on K218b, if confirmed to host life, would provide our first example of biology operating in a sub-Neptune environment. The high atmospheric pressures and different gas compositions could lead to metabolic pathways that have no Earth analogues. Understanding these potential biochemistries requires collaboration between astronomers, chemists, biologists, and other specialists working together to interpret the complex data returned by space telescopes. The question of intelligent life on K218b or similar worlds remains highly speculative. The high probability estimates for life on this planet refer specifically to microbial organisms, not complex multicellular life, let alone intelligent civilizations. The evolution of intelligence appears to require very specific conditions and may be much rarer than simple life forms. Even on Earth, intelligence as we understand it emerged only very recently in the planet's 4.5 billion year history. However, the potential confirmation of any form of life on K218b would have profound implications for the search for intelligent extraterrestrial life. If microbial life proves to be common in the galaxy, it suggests that the basic processes leading to the emergence of life are robust and repeatable. This would increase the probability that some fraction of these worlds might eventually develop more complex forms of life and potentially intelligence. The study of potentially habitable exoplanets like K218b also informs our understanding of Earth's own history and future. By observing worlds at different stages of evolution and under different environmental conditions, astronomers can better understand the processes that have shaped our own planet. These comparative studies help illuminate the factors that have made Earth habitable for billions of years and the challenges that our planet might face in the future. Climate scientists are particularly interested in the atmospheric dynamics of sub-Neptune planets, as these worlds experience greenhouse effects and atmospheric circulation patterns that differ significantly from those on Earth. Understanding how these processes work on alien worlds can provide insights into our own planet's climate system and its sensitivity to changes in atmospheric composition. The search for life on K218b and other exoplanets also drives technological innovation that benefits many other fields of science and engineering. The precision instruments developed for exoplanet observations find applications in medical imaging, environmental monitoring, and industrial quality control. The computational techniques used to analyze exoplanet data contribute to advances in machine learning and artificial intelligence. The international cooperation required for these ambitious projects strengthens scientific partnerships that extend far beyond astronomy. The public fascination with the potential for life on K218b reflects humanity's deep curiosity about our place in the universe and our desire to understand whether we are alone among the stars. This interest helps sustain support for scientific research and education, encouraging young people to pursue careers in science and technology. The search for extraterrestrial life serves as a powerful reminder of the importance of scientific inquiry and the value of exploring the unknown. As observations of K218b continue and our understanding of this remarkable world deepens, scientists remain cautiously optimistic about the possibility of confirming the presence of life. The 99% probability estimate, while based on current understanding of atmospheric chemistry and biological processes, will undoubtedly be refined as more data becomes available. Future observations might strengthen the case for life on this distant world or reveal alternative explanations for the observed atmospheric signatures. Regardless of the ultimate conclusion about K218b specifically, The techniques and technologies being developed to study this world will enable the investigation of hundreds of other potentially habitable exoplanets. Each new world studied adds to our growing catalogue of planetary environments and expands our understanding of the conditions that might support life. The cumulative effect of these studies will be a much more complete picture of life's potential prevalence and diversity throughout the galaxy. The story of K218b represents just the beginning of a new era in the search for life beyond Earth. As more powerful telescopes come online and analytical techniques continue to improve, astronomers will soon be able to study the atmospheres of Earth-sized planets orbiting Sun-like stars. These observations will provide even better analogues to our own world and potentially stronger evidence for biological activity on distant planets. The confirmation of life on any exoplanet would rank among the most significant scientific discoveries in human history, comparable to the development of evolutionary theory or the discovery of the cosmic microwave background radiation. Such a finding would provide definitive proof that life is not unique to Earth and would open entirely new fields of scientific inquiry focused on understanding extraterrestrial biology and ecology. Even in the absence of definitive proof of life, the study of potentially habitable exoplanets like K218b provides valuable insights into the prevalence of Earth-like conditions throughout the galaxy. These studies help constrain estimates of how common life might be and inform strategies for future searches. They also contribute to our understanding of planetary formation and evolution, revealing the physical and chemical processes that determine whether a world becomes habitable or remains sterile. The interdisciplinary nature of exoplanet research brings together experts from many different fields, fostering collaboration and cross-pollination of ideas that often lead to unexpected breakthroughs. Astronomers work alongside biologists to understand what signatures life might produce in planetary atmospheres. Geologists contribute insights into planetary formation and the evolution of surface conditions. Chemists help interpret the complex spectra obtained from distant worlds. Computer scientists develop the algorithms needed to process vast amounts of observational data. This collaborative approach reflects the complexity of the questions being addressed and the need for diverse expertise to tackle such challenging problems. The search for life beyond Earth requires not just technological capabilities, but also theoretical frameworks that can guide observations and help interpret results. The development of these frameworks represents a significant intellectual achievement in its own right, regardless of whether they ultimately lead to the discovery of extraterrestrial life. The ethical and philosophical implications of discovering life on worlds like K218b also deserve careful consideration. How should humanity respond to the confirmation of life beyond Earth? What responsibilities do we have toward other forms of life in the galaxy? How would such a discovery change our understanding of our own species and our place in the cosmic order? These questions become particularly relevant as our technological capabilities continue to advance and the possibility of interstellar travel begins to move from the realm of science fiction toward potential reality. While the distances involved make direct exploration of systems like K218 extremely challenging with current technology, future generations might develop propulsion systems capable of reaching nearby exoplanets within reasonable timeframes. The study of exoplanets also raises questions about planetary protection and the need to preserve potentially habitable worlds from contamination by Earth life or human activities. International agreements already govern the exploration of potentially habitable environments within our own solar system, such as Mars and the icy moons of Jupiter and Saturn. Similar frameworks would need to be developed for exoplanet exploration to ensure that scientific investigations do not inadvertently harm indigenous ecosystems. The economic implications of exoplanet research extend far beyond the direct costs of telescope construction and operation. The technologies developed for these studies drive innovation in multiple industries, from aerospace and defense to telecommunications and computing. The scientific workforce trained in these fields contributes to economic competitiveness and technological leadership. The international partnerships formed around major astronomical projects strengthen diplomatic relationships and foster peaceful cooperation in high-technology endeavors. Educational benefits also flow from the excitement generated by discoveries like the potential life on K2-18b. Public interest in space exploration and astrobiology encourages students to pursue careers in science, technology, engineering, and mathematics. The complex challenges involved in studying exoplanets provide excellent examples for teaching scientific methodology, critical thinking, and the importance of evidence-based reasoning. The cultural impact of discovering life beyond Earth would be profound and long-lasting. Such a discovery would challenge anthropocentric worldviews and encourage a more cosmic perspective on human existence. It would provide concrete evidence that life is a natural phenomenon that emerges under appropriate conditions, rather than a miraculous occurrence unique to our world. This realization could influence art, literature, philosophy, and religion in ways that are difficult to predict but likely to be significant. The timeline for resolving the question of life on K2-18b remains uncertain. While initial observations have provided intriguing hints, definitive confirmation would require additional data and careful analysis to rule out non-biological explanations for the observed atmospheric signatures. The process of scientific verification is necessarily slow and methodical, requiring multiple independent observations and theoretical analyses to build a compelling case. Future observations of K2-18b will likely focus on detecting additional atmospheric gases that could provide stronger evidence for biological activity. The simultaneous presence of oxygen and methane, for example, would be particularly difficult to explain through purely geological processes, as these gases react with each other and would not persist in a planetary atmosphere without continuous replenishment. Other potential biosignatures include specific isotope ratios that might indicate biological fractionation processes, or unusual molecular compounds that would be difficult to produce through non-biological means. The interpretation of these observations will also benefit from improved theoretical models of atmospheric chemistry and planetary evolution. Scientists are developing increasingly sophisticated computer simulations that can predict the atmospheric compositions that might result from different combinations of geological, chemical, and biological processes. These models help guide observational strategies and provide frameworks for interpreting the complex spectra obtained from distant worlds. Laboratory experiments also play a crucial role in understanding potential biosignatures. Researchers are studying the chemical reactions that might occur in sub-Neptune atmospheres under various temperature and pressure conditions. They are also investigating the metabolic pathways that different types of microorganisms might use in environments very different from those found on Earth. These studies help establish the theoretical foundation needed to recognize genuine signs of life when they are observed. The search for life on K2-18b and other potentially habitable exoplanets represents one of the most ambitious scientific endeavors ever undertaken by humanity. It requires the coordination of observations across multiple telescopes, the development of new analytical techniques, and the integration of knowledge from many different scientific disciplines. The scale and complexity of this undertaking reflects the profound importance of the questions being addressed. Success in this endeavor would mark a turning point in human understanding of our place in the universe. The confirmation of life beyond Earth would provide definitive proof that we are not alone and would open new chapters in biology, chemistry, and planetary science. Even if life is not definitively confirmed on K218b, the techniques being developed to study this world will enable the investigation of hundreds of other potentially habitable planets, increasing the chances of eventually making this historic discovery. The story of K218b also illustrates the remarkable progress that has been made in exoplanet science over the past few decades. From the first tentative detections of planets orbiting other stars to the detailed atmospheric analyses possible today, the field has advanced at an extraordinary pace. This progress reflects the dedication of thousands of scientists and engineers working together to push the boundaries of what is possible with current technology. Looking toward the future, the study of exoplanets will continue to benefit from advancing technology and growing international cooperation. New space telescopes with even greater capabilities are being planned, promising to extend our reach to smaller, more Earth-like planets orbiting Sun-like stars. Ground-based telescopes of unprecedented size will provide complementary observations and independent confirmation of space-based results. The development of new analytical techniques will also play a crucial role in advancing our understanding of exoplanet atmospheres. Machine learning algorithms are being developed to help identify subtle patterns in spectroscopic data that might indicate biological activity. Advanced statistical methods are being applied to quantify the probability that observed atmospheric signatures result from living processes rather than purely chemical or physical phenomena. As our catalogue of studied exoplanets grows, scientists will be able to conduct comparative analyses that reveal general patterns and principles governing planetary atmospheres and habitability. These studies will help identify the most promising targets for detailed investigation and will inform the design of future observational campaigns. The cumulative effect of these efforts will be a much more comprehensive understanding of planetary systems and their potential to harbor life. The international character of exoplanet research also deserves recognition. Scientists from around the world contribute their expertise and resources to these ambitious projects, sharing data and collaborating across national boundaries to address questions that affect all of humanity. This cooperation demonstrates science's unique ability to unite people in pursuit of common understanding, transcending political differences and cultural divides. The study of K218b has required contributions from institutions across multiple continents, with astronomers, atmospheric scientists, and astrobiologists working together to analyze the complex data returned by the James Webb Space Telescope. This collaborative approach not only accelerates scientific progress, but also ensures that diverse perspectives and expertise are brought to bear on challenging problems. The international partnerships formed around these projects often lead to lasting relationships that benefit many other areas of scientific research. The philosophical implications of the search for life on K218b extend far beyond the immediate scientific questions. The possibility that life might be common throughout the galaxy challenges traditional assumptions about humanity's unique place in the cosmos. If microbial life exists on a world as different from Earth as K218b, it suggests that the fundamental processes leading to the emergence of life are robust and repeatable under a wide range of conditions. This perspective encourages a more humble and cosmic view of human existence. Rather than seeing ourselves as the pinnacle of creation or the sole intelligent observers in the universe, we might instead be part of a vast community of living worlds, each contributing to the rich tapestry of cosmic evolution. This shift in perspective could have profound implications for how we view our responsibilities toward our own planet and our relationships with other forms of life. The search for life beyond Earth also highlights the preciousness and fragility of the biosphere we inhabit. As we study the conditions required for life to emerge and persist on distant worlds, we gain a deeper appreciation for the remarkable chain of circumstances that has allowed life to flourish on Earth for billions of years. This understanding can inform our efforts to protect and preserve our own planet's environments and the countless species that share our world. The technical achievements represented by the James Webb Space Telescope and its observations of K2-18b also demonstrate humanity's remarkable capacity for innovation and discovery. The telescope itself represents the culmination of centuries of scientific and technological progress. From the development of the first optical telescopes to the sophisticated infrared detectors and cryogenic cooling systems that enable Webb's unprecedented observations. Each component of the telescope embodies countless individual innovations and breakthrough discoveries. The beryllium mirrors that form Webb's primary mirror were shaped to nanometer precision using advanced manufacturing techniques. The multilayer sunshield that protects the telescope's instruments from solar radiation required the development of new materials and deployment mechanisms. The infrared detectors that capture the faint signals from distant worlds push the boundaries of what is possible with current semiconductor technology. The computational analysis required to interpret Webb's observations of K2-18b also represents a significant achievement in data science and atmospheric modeling. The spectra obtained from the planet's atmosphere contain vast amounts of information encoded in subtle patterns of light and shadow across different wavelengths. Extracting meaningful signals from this data requires sophisticated algorithms and theoretical models that account for the complex physics of stellar radiation, atmospheric absorption, and instrumental battine effects. The process of analyzing exoplanet atmospheres has driven advances in multiple areas of computational science. New statistical techniques have been developed to quantify the uncertainty in atmospheric measurements and to distinguish genuine signals from instrumental noise. Machine learning algorithms are being trained to recognize patterns in spectroscopic data that might indicate the presence of specific molecules or even biological processes. These computational tools find applications far beyond astronomy, contributing to advances in medical diagnostics, environmental monitoring, and industrial quality control. The study of K2-18b also illustrates the importance of theoretical modeling in guiding observational astronomy. Before Webb could detect potential biosignatures in the planet's atmosphere, scientists needed to understand what signatures to look for and how to distinguish them from non-biological processes. This required detailed theoretical work on atmospheric chemistry, planetary evolution, and the potential metabolic pathways that life might use in different environments. Theoretical models of sub-Neptune atmospheres have revealed the complex interplay of factors that determine atmospheric composition and evolution. These models consider the effects of stellar radiation, atmospheric escape, chemical reactions, and potential biological processes to predict what gases might be present in detectable quantities. The agreement between theoretical predictions and Webb's observations of K2-18b provides confidence in both the models and the interpretations of the data. The development of these theoretical frameworks has also revealed the limitations of our current understanding. Many aspects of sub-Neptune planet formation and evolution remain poorly understood, partly because these worlds have no analogues in our own solar system. The study of planets like K2-18b is therefore advancing both observational astronomy and theoretical planetary science, filling crucial gaps in our understanding of how planetary systems form and evolve. The potential for life on K218b has also stimulated research into extremophile organisms and the limits of life on Earth. Scientists are studying organisms that thrive in environments that might be analogous to conditions on sub-Neptune planets, such as high-pressure deep-sea environments or volcanically extreme volcanic springs. Understanding how life adapts to these challenging conditions provides insights into the potential for biology on worlds very different from our own. Research into extremophile organisms has revealed remarkable adaptations that allow life to persist under conditions that would be lethal to most other organisms. Some bacteria can survive temperatures above the boiling point of water, while others thrive in highly acidic or alkaline conditions. Deep-sea organisms have adapted to pressures hundreds of times greater than those at Earth's surface. These discoveries suggest that life might be possible under a much wider range of conditions than previously thought possible. The study of these extreme environments has also revealed novel biochemical pathways that could potentially operate on alien worlds. Some organisms derive energy from chemical reactions involving hydrogen sulfide, methane, or other compounds that are toxic to most forms of life. Others can survive on minimal energy inputs, entering dormant states for extended periods when conditions become particularly challenging. These adaptive strategies could potentially allow life to persist on worlds with very different environmental conditions than those found on Earth. The search for biosignatures on K218b has also highlighted the importance of understanding false positives' non-biological processes that might mimic the signatures of life. Volcanic outgassing, impact events, and complex atmospheric chemistry can all produce gases that might be mistaken for biological products. Distinguishing genuine biosignatures from these alternatives requires careful analysis of multiple atmospheric components and their relative abundances. This challenge has led to the development of increasingly sophisticated criteria for evaluating potential biosignatures. Rather than relying on the detection of any single gas, astrobiologists now focus on combinations of gases that would be difficult to maintain simultaneously through non-biological processes. The simultaneous presence of oxygen and methane, for example, would be particularly compelling evidence for biological activity, as these gases react with each other and would not persist together without continuous replenishment. The study of K218b has also demonstrated the value of long-term monitoring of potentially habitable exoplanets. Atmospheric compositions can change over time due to seasonal variations, geological activity, or potential biological cycles. Multiple observations spread across months or years can reveal patterns that might not be apparent in single snapshots. These temporal variations could provide additional clues about the processes responsible for maintaining atmospheric compositions. Future observations of K218b will likely include attempts to map atmospheric variations across different regions of the planet. If the world is tidally locked to its star, with one hemisphere in perpetual daylight and the other in eternal darkness, the atmospheric composition might vary significantly between these regions. Such variations could provide insights into atmospheric dynamics and potentially reveal biological processes that might be more active in certain regions. The potential discovery of life on K218b has also raised questions about the ethics of studying potentially inhabited worlds. How should humanity approach the investigation of worlds that might harbor life? What precautions should be taken to avoid contamination or harm to indigenous ecosystems? These questions become particularly relevant as technology advances toward the possibility of direct exploration through robotic probes or even crewed missions. Current international agreements governing planetary protection focus primarily on worlds within our own solar system, such as Mars, and the icy moons of Jupiter and Saturn. These agreements require that missions to potentially habitable environments be sterilized to prevent contamination by Earth microorganisms. Similar frameworks would need to be developed for exoplanet exploration, though the vast distances involved make physical contamination much less likely than for solar system exploration. The study of potentially habitable exoplanets also raises broader questions about humanity's responsibilities as the only known technological civilization in our immediate cosmic neighborhood. If life proves to be common throughout the galaxy, we might have obligations to protect and preserve these ecosystems, even if we cannot directly interact with them. Such considerations could influence how we develop interstellar travel capabilities and how we conduct future explorations of distant worlds. The economic impact of exoplanet research extends far beyond the direct costs of telescopes and observing campaigns. The technologies developed for studying distant worlds drive innovation across multiple industries. Advanced manufacturing techniques developed for telescope mirrors find applications in semiconductor fabrication and precision optics. Cryogenic cooling systems designed for space telescopes contribute to advances in medical imaging and quantum computing. The computational techniques used to analyze atmospheric spectra benefit fields ranging from environmental monitoring to pharmaceutical research. The skilled workforce trained in exoplanet research also contributes to economic competitiveness and technological leadership. Graduate students and postdoctoral researchers working on atmospheric modeling, spectroscopic analysis, and theoretical astrophysics develop skills that are highly valued in many high-technology industries. This human capital represents a significant return on investment in fundamental scientific research. The international partnerships formed around major astronomical projects like the James Webb Space Telescope also provide economic benefits through technology transfer and collaborative research. Agreements. Countries that contribute to these projects gain access to cutting-edge technologies and expertise that can benefit their domestic industries. The peaceful cooperation required for these ambitious undertakings also strengthens diplomatic relationships and builds trust between nations. Educational benefits flow from the public excitement generated by discoveries like the potential life on K218b. Young people inspired by these findings are more likely to pursue careers in science, technology, engineering, and mathematics, helping to maintain the skilled workforce needed for continued innovation. The complex challenges involved in studying exoplanets also provide excellent examples for teaching scientific methodology, critical thinking, and the importance of evidence-based reasoning. The story of K218b has captured public imagination in ways that demonstrate science's power to inspire wonder and curiosity about the natural world. Media coverage of Webb's observations has introduced millions of people to concepts in astronomy, planetary science, and astrobiology that might otherwise remain confined to academic circles. This public engagement with science helps maintain support for research funding and encourages broader scientific literacy. The cultural impact of potentially discovering life beyond Earth extends into art, literature, and philosophy. Artists and writers have long been inspired by the possibility of extraterrestrial life, and concrete evidence of biology on distant worlds would undoubtedly stimulate new creative works. The confirmation of life beyond Earth would also influence philosophical and religious thinking about humanity's place in the universe and our relationships with other forms of life. The study of K218b represents just one example of how modern astronomy is addressing some of humanity's most profound questions. The techniques and technologies being developed to study this distant world will enable investigations of hundreds of other potentially habitable planets, each offering its own unique insights into the conditions that might support life. The cumulative effect of these studies will be a much more complete understanding of life's potential prevalence and diversity throughout the cosmos. As observations of K218b continue and analytical techniques improve, scientists remain cautiously optimistic about the possibility of confirming biological activity on this distant world. The 99% probability estimate represents one interpretation of current data, but this assessment will undoubtedly evolve as more observations become available and theoretical understanding advances. Regardless of the ultimate conclusion about K218b specifically, the methods being developed to study this world are advancing our capability to search for life throughout the galaxy. The quest to understand whether life exists beyond Earth represents one of the most ambitious scientific endeavors ever undertaken by our species. It requires international cooperation, technological innovation, and intellectual curiosity on an unprecedented scale. The potential rewards confirming that we are not alone in the universe would rank among the most significant discoveries in human history. Even if definitive proof of life on K218b or other exoplanets remains elusive, the search itself provides immense value. The technologies developed for this quest drive innovation across multiple fields. The international partnerships formed around these projects strengthen peaceful cooperation between nations. The scientific understanding gained from studying distant worlds advances our knowledge of planetary science, atmospheric chemistry, and the conditions necessary for life. The study of potentially habitable exoplanets also provides a unique perspective on our own world and its place in the cosmic order. By observing planets with different sizes, compositions, and environmental conditions, we gain insights into the factors that have made Earth habitable for billions of years. This understanding can inform our efforts to address environmental challenges and preserve our planet's ecosystems for future generations. The James Webb Space Telescope's observations of K218b represent a remarkable achievement in human scientific and technological capability. From our vantage point on a small planet orbiting an ordinary star in an unremarkable galaxy, we have developed the ability to analyze the atmospheric composition of worlds more than 100 light-years away. This capability would have seemed like magic to previous generations, yet it represents the logical culmination of centuries of scientific progress and technological innovation. The potential discovery of life on K218b reminds us that science's greatest achievements often come from collaborative efforts that span decades and involve thousands of individuals working toward common goals. The James Webb Space Telescope itself required contributions from scientists, engineers, and technicians in more than a dozen countries. The analysis and interpretation of its observations draws on expertise from multiple scientific disciplines and institutions around the world. This collaborative approach reflects the international character of modern science and its power to unite people across national and cultural boundaries. The search for life beyond Earth is fundamentally a human endeavor that transcends political differences and speaks to our shared curiosity about our place in the universe. The potential confirmation of life on distant worlds would be a discovery for all humanity, regardless of which nation or institution first makes the observation. The story of K218b also illustrates how scientific understanding evolves through careful observation, theoretical modeling, and peer review. Initial observations suggested the possibility of life on this distant world, but confirming this extraordinary claim requires additional data, independent verification, and careful consideration of keen alternative explanations. This methodical approach to evaluating evidence ensures that scientific conclusions are based on solid foundations rather than wishful thinking or premature speculation. The process of scientific discovery is often slower and more cautious than popular media coverage might suggest. Headlines proclaiming a 99% chance of life capture public attention, but the reality of scientific investigation involves careful analysis of uncertainties, systematic consideration of alternative hypotheses, and gradual building of evidence over time. This methodical approach, while sometimes frustrating to those eager for definitive answers, helps ensure that scientific conclusions are reliable and well supported. The search for life on K2-18b and other exoplanets also demonstrates the value of fundamental scientific research that may not have immediate practical applications. When the first exoplanets were discovered in the 1990s, few could have predicted that within a few decades we would be analyzing their atmospheres for signs of life. The techniques and technologies that enable these observations grew out of basic research in physics, chemistry, and engineering that was conducted without specific applications in mind. This history illustrates why support for fundamental scientific research remains crucial for continued progress. The discoveries of tomorrow will likely emerge from today's basic research in ways that we cannot yet anticipate. The study of exoplanets has already generated unexpected insights into planetary formation, atmospheric dynamics, and the potential for life in extreme environments. Future discoveries in this field will undoubtedly yield additional surprises that advance our understanding in unpredictable directions. The potential confirmation of life on K2-18b would also represent a triumph of the scientific method and its power to reveal truths about the natural world through careful observation and analysis. The ability to detect and interpret the faint signals from a world more than 100 light-years away demonstrates the remarkable reach and precision of modern scientific instruments and techniques. As we consider the implications of potentially discovering life on K2-18b, we must also acknowledge the limitations of our current understanding. Even if biological activity is confirmed on this distant world, we would know very little about the specific nature of that life. The organisms responsible for potential biosignatures might be microscopic bacteria very different from any life forms found on Earth. They might exist in environments and under conditions that have no terrestrial analogues. Understanding the detailed characteristics of life on K2-18b or other exoplanets would require observational capabilities far beyond what is currently possible. Future space telescopes might be able to provide additional insights into atmospheric chemistry and dynamics, but directly studying extraterrestrial organisms would likely require technological advances that are still decades or centuries away. The detection of life, if confirmed, would represent just the beginning of a much longer journey toward understanding the nature and diversity of biology throughout the universe. The study of K2-18b has already provided valuable insights into the atmospheric chemistry and evolution of sub-Neptune planets, regardless of whether life is ultimately confirmed on this world. These insights contribute to our understanding of planetary formation and the conditions that determine whether worlds become habitable or remain sterile. Such knowledge is essential for assessing the prevalence of potentially habitable environments throughout the galaxy and for guiding future searches for life. The techniques developed for studying K2-18b are being applied to dozens of other potentially habitable exoplanets discovered by the James Webb Space Telescope and other observatories. Each new world studied adds to our growing catalogue of atmospheric compositions and planetary environments. This comparative approach will eventually reveal general patterns and principles governing planetary atmospheres and their potential to support life. The cumulative effect of these studies will be a much more comprehensive understanding of habitability throughout the cosmos. Rather than focusing on individual worlds that might harbor life, scientists will be able to assess the statistical likelihood that life exists somewhere in the galaxy based on the prevalence of suitable environments and the apparent ease with which biological processes can emerge under appropriate conditions. This statistical approach to astrobiology represents a significant evolution from earlier searches for extraterrestrial life that focused primarily on detecting direct signals from technological pre-civilizations. The study of exoplanet atmospheres provides a way to search for any form of life, from simple microorganisms to complex ecosystems, without requiring that the organisms possess technology or intelligence. The potential discovery of microbial life on worlds like K218b would have profound implications for our understanding of intelligence and its prevalence in the universe. If simple life proves to be common throughout the galaxy, it suggests that the basic processes leading to biology are robust and repeatable. However, the evolution of intelligence might require much more specific conditions and could be significantly rarer than simple life forms. This possibility raises intriguing questions about the future evolution of intelligence in the universe. If Earth-like intelligence is extremely rare, our species might have special responsibilities as potentially one of the few technological civilizations in our galaxy. Alternatively, if intelligence emerges commonly from microbial beginnings, the galaxy might eventually become populated with numerous technological species, leading to very different implications for humanity's cosmic future. The search for life on exoplanets like K218b also provides a new context for considering the factors that have shaped life's evolution on Earth. By studying the conditions on other potentially habitable worlds, scientists can better understand which aspects of Earth's environment have been crucial for the development of complex life and intelligence. This comparative approach could reveal whether features like plate tectonics, large moons, or specific atmospheric compositions are necessary for the evolution of complex organisms. The James Webb Space Telescope's study of K218b represents a remarkable moment in the history of human exploration and discovery. For the first time, we have the technological capability to search for signs of life on worlds orbiting other stars, bringing us closer to answering one of the most fundamental questions about our place in the universe. Whether or not life is ultimately confirmed on this particular world, the techniques and insights gained from studying it will guide the search for life throughout the cosmos for generations to come. The potential 99% probability of life on K218b, while attention-grabbing, represents just one possible interpretation of complex atmospheric data. The true significance of this discovery lies not in any specific probability estimate, but in the demonstration that we now possess the tools and knowledge necessary to search for life throughout the galaxy. Each world we study brings us closer to understanding the prevalence and nature of life in the universe, regardless of whether any individual planet proves to harbor biological activity. As we stand on the threshold of potentially confirming life beyond Earth, we are reminded of the remarkable journey that has brought us to this point. From ancient astronomers who first realized that stars were distant suns, to the development of telescopes that revealed the vastness of the cosmos, to the recent technological achievements that enable us to study the atmospheres of distant worlds, each generation has built upon the discoveries of those who came before. The story of K218b embodies humanity's greatest qualities: our insatiable curiosity about the natural world, our ability to work together across cultural and national boundaries in pursuit of knowledge, and our capacity to develop technologies that extend our senses far beyond their natural limits. Whether or not this distant world harbors life, the quest to understand it has already enriched our knowledge and demonstrated the remarkable power of scientific inquiry. The universe that emerges from our studies of exoplanets like K218b is one of almost incomprehensible diversity and complexity. Planets exist in configurations that were never imagined before their discovery, orbiting stars of every conceivable type under conditions that range from the familiar to the utterly alien. In this vast cosmic laboratory, the processes that govern planetary formation, atmospheric evolution, and potentially the emergence of life play out on billions of worlds across our galaxy alone. The possibility that life might be common throughout this cosmic expanse would transform our understanding of our own significance and responsibility. Rather than being alone in the universe, we might be part of a vast community of living worlds, each contributing to the rich tapestry of cosmic evolution. This perspective encourages humility about our place in the natural order, while simultaneously inspiring awe at the remarkable processes that have given rise to complexity and consciousness in the universe. The search for life on worlds like K218b ultimately reflects humanity's deepest aspirations and most profound questions. In seeking to understand whether we are alone in the universe, we are also seeking to understand ourselves and our place in the cosmic story. The techniques we develop and the discoveries we make in this quest advance not only scientific knowledge, but also our perspective on what it means to be human in an infinite and mysterious cosmos. As the James Webb Space Telescope continues its observations and future instruments extend our reach even further into the galaxy, we stand at the beginning of what may prove to be the most significant era of discovery in human history. The confirmation of life beyond Earth, when it comes, will mark not an end but a beginning, the start of a new chapter in our understanding of life's place in the universe and our responsibilities as conscious beings in a cosmos that may be far more alive than we ever dared to imagine. The ongoing analysis of K218b's atmosphere continues to yield new insights with each passing observation. Scientists have begun to map the three-dimensional structure of the planet's atmosphere, revealing complex circulation patterns that transport gases and heat around the globe. These atmospheric dynamics provide crucial context for understanding how potential biological processes might influence the planet's overall chemical balance. The circulation patterns on K218b are likely very different from those found on Earth or other planets in our solar system. The planet's larger size and higher mass create stronger gravitational forces that could affect how atmospheric gases move and mix. The close proximity to its red dwarf star might also create extreme temperature gradients between the day and night sides of the planet. If it is tidally locked, driving powerful atmospheric currents that could redistribute heat and chemicals across the globe. Understanding these atmospheric dynamics is essential for interpreting the biosignature candidates detected by Webb. If biological processes are indeed responsible for maintaining methane levels in the atmosphere, the efficiency of atmospheric mixing would determine how quickly these gases spread throughout the planet's envelope. Rapid mixing would create relatively uniform concentrations of biologically produced gases, while slow mixing might lead to regional variations that could provide additional clues about the location, nature of potential biological activity. The temperature structure of K218b's atmosphere also holds important clues about the planet's potential habitability. Webb's observations have revealed that the planet's atmospheric temperature varies with altitude, in ways that suggest the presence of distinct atmospheric layers. These layers might include regions where water vapor condenses into clouds, creating weather systems that could influence surface conditions and potentially provide additional environments where life might thrive. The possibility of cloud formation on K218b introduces another layer of complexity to the planet's atmospheric chemistry. Clouds can shield surface regions from harmful stellar radiation while also affecting the global temperature balance through their influence on how much starlight reaches the planet's surface. The composition of these clouds, whether they consist primarily of water droplets, ice crystals, or other chemical compounds, could significantly influence the planet's habitability and the chemical reactions that occur in its atmosphere. Recent theoretical work has suggested that sub-Neptune planets like K218b might possess layered atmospheres with distinct chemical zones at different altitudes. The upper atmosphere might be dominated by lighter gases like hydrogen and helium, while denser regions closer to the surface could contain higher concentrations of water vapor, carbon dioxide, and other compounds more directly relevant to potential biological processes. This stratification could create multiple environments within a single planetary atmosphere, each with its own unique conditions and potential for harboring life. The study of K218b has also revealed the importance of stellar activity in shaping exoplanet atmospheres. Red dwarf stars like K218 are known to produce powerful stellar flares that can dramatically increase their energy output for brief periods. These flares emit high-energy radiation and charged particles that could strip away planetary atmospheres over time, or trigger chemical reactions that might mimic biological signatures. Understanding the history of stellar activity around K218 is therefore crucial for assessing the long-term stability of any potential biosphere on K218b. If the star has been particularly active in the past, it might have already stripped away much of the planet's original atmosphere, leaving behind only the most tightly bound gases. Alternatively, a relatively quiet stellar environment might have allowed complex atmospheric chemistry to develop over billions of years. The magnetic field of K218b, if it exists, would play a crucial role in protecting the planet's atmosphere from stellar radiation and charged particles. Earth's magnetic field deflects much of the harmful radiation from our Sun, creating a protective cocoon that helps preserve our atmosphere and shield surface life from dangerous cosmic rays. The strength and configuration of K218b's magnetic field, if present, would depend on the planet's internal structure and composition, factors that remain largely unknown. Theoretical models suggest that planets with substantial rocky cores and active internal dynamics might generate strong magnetic fields through the same processes that create Earth's magnetosphere. However, the larger size and different composition of sub-Neptune planets could lead to very different magnetic field configurations. Some models suggest that these worlds might have weaker magnetic fields or field geometries that provide less effective protection against stellar radiation. But the potential for life on K218b has also stimulated new research into the biochemical pathways that organisms might use in high-pressure, hydrogen-rich environments. Traditional Earth biochemistry relies heavily on reactions involving oxygen, but life in a sub-Neptune atmosphere might need to utilize very different chemical processes. Some researchers have proposed that organisms might derive energy from reactions involving hydrogen gas, which would be abundant in K218b's atmosphere. These hypothetical biochemical pathways could produce waste products very different from those created by terrestrial life forms. Instead of oxygen, which is produced by photosynthesis on Earth, alien organisms might release hydrogen sulfide, ammonia, or other compounds as byproducts of their metabolism. Identifying these alternative biosignatures requires expanding our conception of what life might look like under conditions very different from those found on Earth. The search for these alternative biosignatures has led to increased collaboration between astronomers and biochemists working to understand the fundamental constraints on biological processes. Laboratory experiments are being conducted to investigate how known terrestrial organisms respond to high-pressure, hydrogen-rich conditions similar to those that might exist on K2-18b. While these experiments cannot perfectly replicate alien environments, they provide valuable insights into the limits of biological adaptability. Some of the most intriguing results have come from studies of extremophile organisms that thrive in Earth's most challenging environments. Researchers have discovered bacteria that can survive and even grow under pressures hundreds of times greater than Earth's surface atmospheric pressure. Other organisms have been found to metabolize hydrogen gas directly, using it as an energy source in environments where more traditional biochemical pathways would be impossible. These discoveries suggest that life might be more adaptable to extreme conditions than previously thought. If terrestrial organisms can survive under conditions that approximate some aspects of sub-Neptune environments, it seems plausible that life could evolve specifically for such conditions given sufficient time and calor. Appropriate starting materials. The possibility of life in K2-18b's atmosphere has also raised questions about how such organisms might reproduce and maintain stable populations. On Earth, most life forms rely on solid surfaces or liquid environments for reproduction and population growth. In a thick, gaseous atmosphere, potential organisms might need to develop very different strategies for reproduction and survival. Some researchers have speculated that atmospheric life forms might exist as floating colonies of microorganisms, similar to the microbial mats found in some terrestrial environments. These colonies could maintain themselves through cooperative behaviors, with different species contributing specialized functions to the overall community. Such communities might be able to regulate their buoyancy to remain at optimal altitudes within the atmosphere, where temperature, pressure, and chemical conditions are most favorable for their survival. The energy sources available to potential atmospheric life forms on K2-18b would likely be very different from those used by terrestrial organisms. Photosynthesis, which powers much of Earth's biosphere, might be challenging in the thick atmosphere of a sub-Neptune planet where sunlight could be heavily filtered by atmospheric gases and particles. Alternative energy sources might include chemical reactions involving atmospheric gases or even heat generated by the planet's internal radioactive decay. The concept of chemosynthetic life forms that derive energy from chemical reactions rather than sunlight is well established on Earth. Deep-sea hydrothermal vents host thriving ecosystems based entirely on chemosynthesis, with organisms that convert hydrogen sulfide and other chemicals into usable energy. Similar processes might operate in the atmospheres of sub-Neptune planets, where a rich variety of chemical compounds could provide energy for biological processes. The study of K2-18b has also highlighted the importance of temporal variations in atmospheric composition. Earth's atmosphere undergoes daily, seasonal, and longer-term changes driven by biological processes, geological activity, and astronomical cycles. Similar variations on K2-18b could provide additional evidence for biological activity, particularly if they follow patterns that would be difficult to explain through purely physical or chemical. Quote, processes. Seasonal variations, if they exist on K2-18b, would likely be very different from those experienced on Earth. The planet's orbit around its red dwarf star takes just 33 days, meaning that any seasonal cycles would occur much more rapidly than Earth's annual pattern. However, other factors such as changes in stellar activity or long-term variations in atmospheric circulation could create temporal patterns in atmospheric composition that might be detectable by sensitive PEEN instruments. The detection of periodic variations in biosignature gases could provide particularly compelling evidence for biological activity. On Earth, the concentration of carbon dioxide in the atmosphere varies seasonally as plants absorb the gas during photosynthesis in spring and summer, then release it during fall and winter when vegetation dies. Similar cyclical patterns in the atmospheres of exoplanets could indicate large-scale biological processes. The search for temporal variations in K2-18b's atmosphere requires long-term monitoring campaigns that observe the planet repeatedly over months or years. The James Webb Space Telescope's observing schedule allows for such repeated observations, though telescope time is extremely valuable and must be allocated carefully among competing scientific priorities. The potential significance of confirming biological activity on K2-18b has justified substantial allocation of observing time to this target. Future observations of K2-18b will likely focus on detecting additional atmospheric components that could strengthen the case for biological activity. Phosphine, for example, is produced by some terrestrial organisms and would be particularly difficult to explain through non-biological processes in the atmospheric conditions expected on K2-18b. The detection of phosphine in combination with the already identified water vapor, carbon dioxide, and methane would create an even more compelling biosignature profile. Other potentially significant atmospheric components include ammonia, which could be produced by nitrogen metabolizing organisms, and various organic compounds that might be byproducts of biological processes. Each additional biosignature candidate detected would strengthen the overall case for life, while also providing clues about the nature and metabolism of potential organisms. The analytical techniques used to study K2-18b's atmosphere are constantly being refined and improved. New computational methods are being developed to extract more information from the same observational data. While advances in theoretical modeling help scientists better understand how different atmospheric processes might affect the signals they observe. These improvements in analytical capability effectively increase the sensitivity of existing observations and could reveal additional biosignature candidates that were not apparent in initial analyses. Machine learning algorithms are playing an increasingly important role in exoplanet atmospheric analysis. These computational tools can identify subtle patterns in spectroscopic data that might be missed by traditional analysis methods. They can also help distinguish genuine atmospheric signatures from instrumental artifacts or noise, increasing confidence in the detection of trace gases that might indicate biological activity. The development of these machine learning tools requires training on large datasets of both real and simulated atmospheric spectra. Researchers are creating extensive libraries of theoretical spectra that represent different possible atmospheric compositions and conditions, allowing algorithms to learn to recognize the signatures of various gases under different circumstances. This approach helps ensure that automated analysis methods are robust and reliable when applied to precious observational data from space telescopes. The study of K2-18b has also contributed to our understanding of the broader population of sub-Neptune exoplanets. Observations of similar worlds have revealed a surprising diversity of atmospheric compositions and properties, suggesting that planet formation and evolution processes can lead to very different outcomes even for planets of similar size and orbital characteristics. Some sub-Neptune planets appear to have retained thick hydrogen-dominated atmospheres similar to smaller versions of gas giants like Neptune. Others seem to have lost much of their original atmospheric hydrogen, leaving behind atmospheres dominated by heavier gases like water vapor and carbon dioxide. These differences likely reflect variations in stellar radiation, planetary formation history, and internal heat sources. Understanding this diversity is crucial for assessing the potential habitability of sub-Neptune planets as a class. If most of these worlds have atmospheric conditions that are hostile to life as we know it, then K218b might represent an unusual exception rather than a typical example. Alternatively, if many sub-Neptune planets possess atmospheric conditions conducive to biological processes, the potential for life in the galaxy could be much greater than previously estimated. The comparative study of sub-Neptune atmospheres has revealed several factors that appear to influence their composition and evolution. Planets orbiting closer to their stars tend to have lost more of their original atmospheric hydrogen, possibly due to intense stellar radiation that heats and strips away light gases. The mass of the planetary core also appears to play a role, with more massive cores better able to retain substantial atmospheres over geological timescales. These empirical relationships help astronomers identify which sub-Neptune planets are most likely to possess atmospheric conditions favorable for life. Planets like K218b, with intermediate masses and orbits within the habitable zone, appear to represent the most promising targets for detailed atmospheric analysis and biosignature searches. The study of K218b has also influenced the design of future space telescopes specifically intended for exoplanet characterization. The success of Webb's atmospheric observations has demonstrated the value of infrared spectroscopy for studying exoplanet atmospheres, leading to proposals for even more capable infrared PAMID. Observatories. These future telescopes would possess larger mirrors, more sensitive detectors, and specialized instruments optimized for exoplanet observations. The proposed Habitable Exoplanet Observatory represents one such next-generation facility, specifically designed to search for signs of life on potentially habitable worlds. This telescope would focus on studying Earth-sized planets orbiting Sun-like stars, complementing Webb's studies of larger planets around smaller stars. The combination of observations from multiple specialized telescopes would provide a comprehensive survey of potentially habitable exoplanets across a wide range of planetary and stellar types. Ground-based telescopes are also contributing to the study of exoplanet atmospheres, though their observations are limited by Earth's own atmospheric absorption and turbulence. The next generation of extremely large ground-based telescopes, with mirrors 25 to 40 meters in diameter, will possess unprecedented light-gathering power and spatial resolution. These giants will be capable of directly imaging some nearby exoplanets and analyzing their atmospheres independently of space-based observations. The combination of space-based and ground-based observations provides multiple independent methods for confirming atmospheric detections and reduces the risk of systematic errors in any single craft. Observational technique. This multi-platform approach has become standard practice in exoplanet science, where extraordinary claims require extraordinary evidence to gain acceptance by the scientific community. The potential discovery of life on K218b has also stimulated theoretical work on how biological processes might influence planetary evolution over geological timescales. Life on Earth has had profound effects on our planet's atmospheric composition, surface chemistry, and even geological processes. Similar biological influences on K218b could leave signatures that extend beyond simple atmospheric chemistry. Biological processes can affect the isotopic composition of atmospheric gases in ways that are difficult to replicate through purely chemical or physical processes. Living organisms often preferentially incorporate lighter isotopes of key elements like carbon and nitrogen, leaving characteristic isotopic signatures in their waste products and in the atmospheric aurora, gases they consume or produce. Detecting these isotopic signatures on K218b would provide particularly strong evidence for biological activity. The study of isotopic ratios in exoplanet atmospheres pushes the limits of current observational capabilities, requiring extremely high spectroscopic precision to distinguish between different castri, isotopic species. Future telescopes with enhanced sensitivity and spectroscopic resolution will be better equipped to search for these subtle but potentially definitive biosignatures. The potential confirmation of life on K218b would also have implications for astrobiology research beyond exoplanet studies. Understanding how life might emerge and persist in sub-Neptune environments could inform the search for life elsewhere in our own solar system, particularly on the large moons of gas-giant planets that possess substantial atmospheres and possible subsurface oceans. Titan, Saturn's largest moon, possesses a thick, nitrogen-rich atmosphere with organic chemistry that shares some similarities with the conditions that might exist on K218b. While Titan is much colder than K218b and receives far less energy from the Sun, studying the complex organic chemistry in Titan's atmosphere provides insights into the types of chemical processes that might occur in other thick planetary atmospheres. The study of K218b has also contributed to our understanding of how planetary atmospheres respond to different types of stellar radiation. Red dwarf stars like K218 emit most of their energy in infrared wavelengths, creating very different photochemical environments than those found around Sun-like stars. Understanding these differences is crucial for assessing the habitability potential of the billions of planets orbiting red dwarf stars throughout the galaxy. Photochemical processes driven by stellar radiation can both create and destroy potential biosignature gases in planetary atmospheres. Ultraviolet radiation from stars can break down methane and other organic compounds, while also driving chemical reactions that might produce oxygen or other gases that could be mistaken for habitable biological signatures. The balance between these production and destruction processes depends critically on the spectrum and intensity of stellar radiation. The relatively low ultraviolet output of red dwarf stars might actually favor the persistence of organic compounds in planetary atmospheres, as there would be less high-energy radiation to break down complex molecules. This could make red dwarf systems particularly favorable for maintaining atmospheric biosignatures over long time periods, increasing the chances that any biological activity would be detectable by TSE. Astronomical observations. However, red dwarf stars are also known for producing powerful stellar flares that can temporarily increase their ultraviolet output by orders of magnitude. These flare events could have complex effects on planetary atmospheres, potentially triggering chemical reactions that might either enhance or obscure potential biosignatures. Understanding the frequency and intensity of stellar flares from K218 and their potential effects on the planet's atmosphere is an active area of research. The long-term evolution of K218b's atmosphere also depends on the planet's ability to retain its atmospheric gases against various loss processes. The planet's relatively strong gravity helps it hold onto its atmosphere, but stellar radiation and particle bombardment could still cause gradual atmospheric escape over billions of years. The rate of this atmospheric loss would influence how long any potential biosphere could persist on the planet. Theoretical models of atmospheric evolution on sub-Neptune planets suggest that worlds like K218b might undergo dramatic changes in atmospheric composition over their lifetimes. Early in their evolution, these planets might possess massive hydrogen-dominated atmospheres inherited from their formation in the protoplanetary disk. Over time, stellar radiation could gradually strip away lighter gases, leaving behind atmospheres dominated by heavier compounds like water vapor and carbon dioxide. This evolutionary scenario has important implications for the potential development of life on K2-18b. If the planet's current atmospheric composition represents a relatively recent development in its evolution, any life forms present might be relatively young compared to Earth's ancient biosphere. Alternatively, if the planet has maintained stable atmospheric conditions for billions of years, there might have been ample time for complex biological evolution to occur. The search for additional exoplanets with similar properties to K2-18b has intensified following Webb's observations of this world. Astronomers are systematically studying other sub-Neptune planets in the habitable zones of nearby red dwarf stars, looking for atmospheric compositions that might indicate biological activity. This comparative approach will help determine whether K2-18b represents a unique case or part of a broader population of potentially inhabited worlds. The statistical significance of any individual biosignature detection increases dramatically when multiple examples are found. If several sub-Neptune planets show similar atmospheric signatures suggesting biological activity, it would be much more difficult to explain all of these observations through purely chemical or physical processes. The discovery of a population of potentially inhabited worlds would transform our understanding of life's prevalence in the universe. Current surveys have identified dozens of sub-Neptune planets orbiting within the habitable zones of nearby stars, providing a substantial sample for atmospheric characterization studies. Webb's observing capabilities allow detailed atmospheric analysis of the most promising targets, while other telescopes provide supporting observations and broader surveys of planetary populations. The interdisciplinary nature of K2-18b research has brought together experts from diverse fields to address the complex questions raised by potential biosignature detections. Atmospheric chemists work alongside microbiologists to understand what chemical signatures different types of organisms might produce. Planetary scientists collaborate with stellar astronomers to model how different stellar environments might affect planetary habitability. Computer scientists develop the algorithms needed to extract meaningful signals from complex observational data. This collaborative approach reflects the inherently interdisciplinary nature of astrobiology and the need for diverse expertise to tackle such challenging questions. No single scientific discipline possesses all the knowledge needed to assess the potential for life on distant worlds. Success requires integration of insights from multiple fields and careful coordination of different types of observations and analyses. The study of K2-18b has also highlighted the importance of maintaining scientific objectivity and skepticism when evaluating extraordinary claims. The possibility of discovering life beyond Earth generates tremendous excitement among scientists and the public alike. But this enthusiasm must be balanced against the need for rigorous evaluation of evidence and careful consideration of alternative explanations. The scientific community has established protocols for evaluating potential biosignature detections that require multiple independent observations, peer review of analytical methods, and systematic consideration of non-biological explanations. These protocols help ensure that claims of extraterrestrial life are based on solid evidence rather than wishful thinking or premature interpretation of ambiguous data. The debate surrounding the interpretation of K2-18b's atmospheric composition illustrates how the scientific process works to evaluate controversial findings. Initial observations suggesting potential biosignatures have prompted additional observations, alternative analyses of existing data, and theoretical work exploring different possible explanations. This ongoing process of investigation and debate helps build consensus around the most reasonable interpretation of the available evidence. The potential discovery of life on K218b has also raised questions about how such findings should be communicated to the public. Scientific results are often provisional and subject to revision as new data becomes available, but public communication sometimes presents findings as more definitive than they actually are. Balancing the legitimate excitement generated by potential biosignature detections against the need for scientific caution presents ongoing challenges for science communication. Media coverage of K218b has generally emphasized the remarkable nature of potentially detecting life on a distant world, while also noting the preliminary nature of the findings and the need for additional confirmation. This balanced approach helps educate the public about how scientific discoveries emerge through careful investigation rather than sudden revelation. Educational institutions have incorporated the study of K218b into curricula ranging from elementary school through graduate-level courses. The combination of cutting-edge technology, profound scientific questions, and potential implications for understanding our place in the universe makes this discovery an excellent vehicle for teaching about the scientific method, astronomical observations, and astrobiology. The story of K218b also provides opportunities to discuss the international nature of modern scientific research and the importance of peaceful cooperation in addressing humanity's greatest challenges. The James Webb Space Telescope represents a collaboration among multiple space agencies and countries, demonstrating how shared scientific goals can unite people across cultural and political boundaries. As observations of K218b continue and analytical techniques improve, the scientific community remains committed to pursuing the truth about this distant world, regardless of whether that truth confirms or refutes the possibility of life. The ultimate goal is understanding, no confirmation of any particular hypothesis. This commitment to following the evidence wherever it leads exemplifies the best traditions of scientific inquiry. The legacy of K218b research will likely extend far beyond the question of whether this particular world harbors life. The techniques developed to study this planet are advancing our general capability to investigate exoplanet atmospheres and search for biosignatures throughout the galaxy. Future discoveries will build upon the foundations established through the intensive study of this remarkable world. Whether K218b ultimately proves to harbor life or not, its study has already expanded our understanding of planetary atmospheres, stellar-planetary interactions, and the potential for life in environments very different from Earth. These insights contribute to the broader scientific enterprise of understanding how planets form and evolve, and what conditions might be necessary for life to emerge and persist in the universe. The quest to understand K218b continues to inspire new generations of scientists and engineers who will push the boundaries of what is possible in astronomical observations and analysis. The technologies and techniques being developed today will enable even more ambitious investigations of distant worlds in the decades to come, bringing us ever closer to answering one of humanity's most profound questions about our place in the cosmos. The methodical approach to studying K218b reflects the careful, systematic nature of modern astronomical research. Each observation must be planned months in advance, with precise calculations determining when the planet will be optimally positioned for spectroscopic analysis. The James Webb Space Telescope's complex pointing system must track the planet's motion across the sky with extraordinary precision, maintaining perfect alignment for hours at a time while the delicate instruments collect the faint signals from this distant world. The data collection process itself represents a triumph of engineering and computational science. Webb's detectors convert incoming photons into digital signals that are processed by onboard computers, compressed for transmission, and beamed across the vast distance between the telescope and Earth. Ground stations around the world receive these precious data packages, which are then distributed to research teams for analysis and interpretation. The volume of data generated by a single observation of K218b is staggering, containing millions of individual measurements across different wavelengths of light. Each measurement carries information about the planet's atmospheric composition, temperature structure, and dynamics. Extracting meaningful scientific insights from this flood of information requires sophisticated computational tools and deep expertise in atmospheric physics and chemistry. A calibration of Webb's instruments represents another crucial aspect of ensuring reliable results. The telescope's detectors must be precisely characterized to understand how they respond to light of different wavelengths and intensities. Any systematic errors in this calibration could lead to spurious signals that might be mistaken for atmospheric features. Teams of instrument scientists work continuously to monitor and improve the telescope's calibration, ensuring that the data quality meets the exacting standards required for biosignature detection. The statistical analysis of K218b's atmospheric data involves complex mathematical techniques designed to distinguish genuine signals from random noise and systematic artifacts. Researchers employ Bayesian statistical methods that quantify the probability that observed features represent real atmospheric components rather than instrumental effects or chance variations. These analyses must account for numerous sources of uncertainty, from photon noise in the detectors to possible variations in the planet's atmospheric conditions during the observation. The peer review process for K218b research exemplifies the rigorous standards applied to extraordinary scientific claims. Papers reporting potential biosignatures undergo intensive scrutiny by independent experts who examine every aspect of the observations, analysis methods, and interpretation. This process can take many months and often results in requests for additional observations, alternative analyses, or more detailed consideration of possible systematic errors. The replication and verification of K218b results has involved multiple independent research teams analyzing the same observational data using different computational methods and theoretical frameworks. This approach helps identify any biases or errors that might be introduced by particular analysis techniques. When multiple independent analyses reach similar conclusions, confidence in the results increases substantially. The theoretical modeling of K218b's atmosphere has evolved considerably as observational constraints have improved. Early models based on general principles of atmospheric physics have been refined to incorporate specific observational findings about the planet's temperature structure, chemical composition, and dynamics. These increasingly sophisticated models help scientists understand how different physical and chemical processes might contribute to the observed atmospheric properties. Three-dimensional atmospheric circulation models of K218b reveal complex patterns of gas transport that could significantly influence the distribution of potential biosignatures. These models suggest that the planet's thick atmosphere might support powerful jet streams and circulation cells that redistribute heat and chemical species around the globe. Understanding these circulation patterns is crucial for interpreting point observations of atmospheric composition in the context of global atmospheric processes. The chemical kinetics models used to interpret K218b's atmospheric composition must account for hundreds of possible chemical reactions involving dozens of different molecular species. The rates of these reactions depend on temperature, pressure, and the presence of catalysts, all of which vary throughout the planet's atmosphere. Advanced computational methods are required to solve the complex system of differential equations that describes how atmospheric chemical composition evolves over time. Photochemical modeling of K218b's atmosphere considers how stellar radiation drives chemical reactions that could either produce or destroy potential biosignature gases. The relatively low ultraviolet output of the planet's red dwarf host star creates a very different photochemical environment than that found around Sun-like stars. These differences could have important implications for which biosignature gases might persist in detectable quantities and which might be rapidly destroyed by atmospheric chemistry. The study of analog environments on Earth has provided valuable insights into the types of atmospheric chemistry that might occur on K218b. Researchers have conducted laboratory experiments simulating high-pressure, hydrogen-rich atmospheric conditions similar to those expected on sub-Neptune planets. These experiments reveal how different chemical species interact under extreme conditions and help validate the reaction rates used in theoretical models. Field studies of Earth's most extreme environments continue to expand our understanding of life's limits and the biosignatures it might produce under conditions very different from those in typical terrestrial keen environments. Research in high-pressure deep-sea environments, highly acidic volcanic springs, and other extreme locations reveals the remarkable adaptability of life and the diverse chemical signatures that different types of organisms can produce. The discovery of new extremophile organisms on Earth regularly expands the range of conditions considered potentially habitable. Recent discoveries include bacteria that thrive at temperatures exceeding 120 degrees Celsius, organisms that survive in bashka, solutions more acidic than battery acid, and microbes that generate energy from chemical reactions involving radioactive elements. Each new discovery broadens the conceivable range of environments where life might exist on distant worlds. The biomolecular analysis of extremophile organisms has revealed novel metabolic pathways that could potentially operate in the atmospheric conditions expected on K218b. Some organisms derive energy from reactions involving molecular hydrogen, which would be abundant in a sub-Neptune atmosphere. Others utilize sulfur compounds or metal ions in ways that could potentially produce atmospheric signatures detectable by space telescopes. The isotopic signatures produced by different metabolic pathways provide another potential avenue for confirming biological activity on K218b. Living organisms often exhibit preferences for lighter isotopes of key elements, creating characteristic isotopic ratios in their waste products and in the atmospheric gases they consume or produce. Detecting these subtle isotopic signatures requires extraordinary spectroscopic precision, but could provide particularly compelling evidence for biological processes. The development of new observational techniques specifically designed for biosignature detection continues to advance the field of exoplanet atmospheric analysis. High-resolution spectroscopy can resolve individual molecular absorption lines, providing more detailed information about atmospheric composition and enabling the detection of trace gases at lower Ba concentrations. Polarimetry analyzes the polarization of light reflected or transmitted by planetary atmospheres, potentially revealing information about atmospheric particles and cloud properties. The coordination of observations across multiple telescopes and wavelength ranges provides complementary information about K2-18b's atmospheric properties. Radio observations can probe different atmospheric layers than infrared spectroscopy, while ultraviolet observations reveal photochemical processes occurring in the planet's upper atmosphere. Combining results from different observational techniques creates a more complete picture of the planet's atmospheric structure and composition. The timing of observations relative to the planet's orbital phase can reveal variations in atmospheric properties between different regions of the planet. If K2-18b is tidally locked to its star, observations during different parts of its orbit would sample different hemispheres of the planet, potentially revealing atmospheric variations between the second T, permanently illuminated and dark sides of the world. The surge for variability in K2-18b's atmospheric composition over different timescales provides another test of potential biological activity. Biological processes often create temporal variations in atmospheric chemistry, whether through daily cycles of photosynthesis and respiration, seasonal changes in biological activity, or longer-term evolutionary changes in ecosystems. Detecting such variability would provide additional evidence for biological rather than purely chemical or physical processes. The development of increasingly sophisticated atmospheric retrieval algorithms has improved scientists' ability to extract accurate atmospheric compositions from complex spectroscopic data. These algorithms use advanced statistical methods to find the atmospheric models that best match the observed spectra while accounting for various sources of uncertainty and potential systematic errors. The continuous refinement of these techniques increases the reliability of atmospheric composition measurements. Machine learning approaches to atmospheric analysis have shown particular promise for identifying subtle patterns in spectroscopic data that might be missed by traditional analysis methods. Neural networks trained on large datasets of simulated atmospheric spectra can learn to recognize the signatures of different atmospheric components even when those signatures are weak or partially obscured by other atmospheric features. The application of artificial intelligence to K2-18b data analysis has helped identify potential atmospheric features that were not immediately apparent in initial analyses. These AI-assisted discoveries must still be validated through traditional analytical methods, but the ability of machine learning algorithms to process vast amounts of data and identify subtle patterns has proven valuable for maximizing the scientific return from precious telescope observations. The database of exoplanet atmospheric observations continues to grow as more planets are studied with increasingly sophisticated instruments. This expanding dataset enables comparative studies that reveal general patterns in atmospheric composition and evolution across different types of planets and stellar environments. Such comparative analyses help place individual discoveries like K2-18b in broader context and improve our understanding of planetary atmospheric processes. The characterization of planetary atmospheres around different types of stars is revealing how stellar properties influence the chemical environments of orbiting planets. Planets around red dwarf stars like K2-18 show different atmospheric characteristics than those orbiting Sun-like stars, reflecting the different spectral energy distributions and activity patterns of their host stars. Understanding these relationships helps astronomers predict which types of planetary systems are most likely to harbor detectable biosignatures. The study of atmospheric escape processes on sub-Neptune planets like K2-18b has revealed the complex interplay between stellar radiation, planetary gravity, and atmospheric retention. Some planets lose their atmospheres rapidly when subjected to intense stellar irradiation, while others retain substantial atmospheric envelopes for billions of years. The factors that determine atmospheric retention have important implications for long-term habitability and the persistence of any potential biosignatures. Theoretical work on the formation and evolution of sub-Neptune planets has provided crucial context for understanding K2-18b's current properties. These planets likely formed farther from their stars and then migrated inward to their current orbits, potentially undergoing dramatic changes in atmospheric composition during this migration process. Understanding this evolutionary history helps scientists interpret current atmospheric observations and assess the likelihood that favorable conditions for life have persisted over geological timescales. The role of planetary moons in influencing habitability has also been considered in the context of K2-18b, though no moons have been detected around this distant world. Large moons can affect planetary atmospheres through tidal heating, orbital dynamics, and magnetic field interactions. The presence or absence of substantial moons could influence a planet's long-term atmospheric stability and climate evolution. The possibility of atmospheric biosignatures produced by subsurface life represents another avenue of investigation relevant to K2-18b. Even if the planet's surface conditions are not directly habitable, subsurface environments might harbor life forms that release gases into the atmosphere. This scenario has parallels with potential subsurface biospheres on Mars and the icy moons of the outer solar system. The development of next-generation space telescopes specifically designed for exoplanet characterization promises to revolutionize our ability to study worlds like K2-18b. These future observatories will possess larger mirrors, more sensitive detectors, and specialized instruments optimized for detecting and analyzing exoplanet atmospheres. The increased sensitivity and capability of these telescopes will enable the study of smaller planets and the detection of more subtle biosignature gases. The Habitable Exoplanet Observatory, currently in the early planning stages, represents one such next-generation facility designed specifically to search for signs of life on potentially habitable worlds. This telescope would focus on Earth-sized planets orbiting Sun-like stars, complementing Webb studies of larger planets around smaller stars. The combination of observations from multiple specialized telescopes would provide comprehensive coverage of potentially habitable exoplanets across a wide range of planetary and stellar parameters. Ground-based extremely large telescopes currently under construction will also contribute significantly to exoplanet atmospheric studies. These telescopes, with mirrors 25 to 40 meters in diameter, will possess unprecedented light-gathering power and spatial resolution. Their large size will enable direct imaging of some nearby exoplanets, allowing atmospheric analysis without relying on transit observations. The combination of space-based and ground-based observations provides multiple independent methods for confirming atmospheric detections and reduces the risk of systematic errors in any single PRADE. Observational approach. This multi-platform strategy has become essential for building confidence in extraordinary claims like the potential detection of life on distant worlds. The international partnerships required for these ambitious observational programs demonstrate science's power to unite people across national and cultural boundaries in pursuit of common understanding. The James Webb Space Telescope itself represents collaboration among space agencies from the United States, Europe, and Canada, with contributions from scientists and engineers around the world. Future exoplanet missions will likely involve even broader international cooperation. The technological spillovers from exoplanet research continue to benefit many other fields of science and technology. Advances in detector sensitivity, precision optics, and computational analysis developed for exoplanet studies find applications in medical imaging, environmental monitoring, telecommunications, and numerous other areas. The investment in fundamental research for exoplanet characterization generates economic and technological benefits that extend far beyond astronomy. The educational impact of K218b research has been substantial, inspiring students at all levels to pursue careers in science, technology, engineering, and mathematics. Universities around the world have developed new courses and research programs focused on astrobiology and exoplanet science. The interdisciplinary nature of this research provides excellent training for students, exposing them to diverse scientific methods and fostering collaboration across traditional disciplinary boundaries. The public engagement aspects of K218b research have helped maintain support for fundamental scientific research and space exploration. Public interest in the search for life beyond Earth provides a compelling narrative for communicating the value of scientific inquiry and international cooperation. This public support is crucial for sustaining the long-term funding commitments required for ambitious space telescope missions. The philosophical implications of potentially discovering life on K218b continue to stimulate discussion among scientists, philosophers, and the broader public. Such a discovery would provide concrete evidence that life is not unique to Earth and would raise profound questions about the prevalence of life throughout the universe. These discussions help contextualize scientific discoveries within broader frameworks of human understanding and meaning. The ethical considerations surrounding the study of potentially inhabited worlds also deserve ongoing attention. How should humanity respond to the confirmation of life beyond Earth? What responsibilities do we have toward other forms of life in the galaxy? How should we conduct future explorations to minimize potential harm to indigenous ecosystems? These questions will become increasingly relevant as our technological capabilities advance. The long-term implications of confirming life on K218b or similar worlds extend far beyond immediate scientific impact. Such discoveries could influence human culture, philosophy, and our sense of place in the universe for generations to come. They might also affect how we approach environmental protection on Earth and our relationships with other species that share our planet. The timeline for definitive resolution of the life question on K218b remains uncertain, reflecting both the complexity of the scientific challenges involved and the need for careful verification of TAEUS. Extraordinary claims. Additional observations with Webb and other telescopes will continue to refine our understanding of the planet's atmospheric composition and dynamics. Future telescopes with enhanced capabilities may provide even more definitive evidence for or against biological activity. The broader search for life in the universe will continue regardless of the ultimate conclusion about K218b specifically. Hundreds of other potentially habitable exoplanets await detailed atmospheric characterization, each offering its own unique insights into the conditions that might support life. The techniques and expertise developed through studying K218b will guide investigations of these other worlds and help build a comprehensive understanding of life's potential prevalence throughout the galaxy. The story of K218b represents a remarkable chapter in humanity's ongoing quest to understand our place in the cosmos. Whether this distant world harbors life or not, its study has already advanced our knowledge of planetary science, atmospheric chemistry, and the potential for life in extreme environments. The technological achievements that enable these studies demonstrate our species' remarkable capacity for innovation and discovery. As we continue to push the boundaries of what is possible in astronomical observation and analysis, we move closer to answering one of the most profound questions that has captivated human imagination throughout history. The potential confirmation of life beyond Earth would mark a watershed moment in human understanding, opening new chapters in biology, chemistry, and our conception of life's place in the universe. The legacy of K2-18b research will endure long beyond any individual discovery or observation. The methods developed to study this world are advancing our general capability to investigate exoplanet atmospheres and search for biosignatures throughout the galaxy. Future generations will build upon these foundations to explore even more distant worlds and perhaps eventually make direct contact with the life forms that may populate our cosmic neighborhood. In contemplating the vast distances that separate us from worlds like K2-18b, we are reminded of both our cosmic isolation and our connection to the broader universe. The same physical laws that govern atmospheric chemistry on this distant world also operate in our own atmosphere. The carbon, oxygen, and other elements that might support life on K2-18b were forged in the cores of ancient stars, just as the elements in our own bodies were created through stellar nuclear synthesis billions of years ago. This cosmic perspective encourages humility about our place in the natural order, while simultaneously inspiring awe at the remarkable processes that have given rise to complexity and consciousness in the universe. Whether we are alone or part of a vast community of living worlds, the search for life on planets like K2-18b helps us understand our own existence and our responsibilities as conscious beings in an magnificent and mysterious cosmos. The detailed spectroscopic analysis of K2-18b's atmosphere has revealed subtle features that continue to intrigue researchers months after the initial observations. Beyond the prominent signatures of water vapor, carbon dioxide, and methane, fainter absorption lines suggest the presence of trace gases that could provide additional clues about the planet's atmospheric chemistry and potential biological activity. These weak signals require careful analysis to distinguish them from instrumental noise and systematic effects. The process of identifying trace atmospheric components involves sophisticated pattern recognition techniques that search for the characteristic fingerprints of different molecules across the entire observed spectrum. Each chemical compound absorbs light at specific wavelengths determined by its molecular structure and quantum mechanical properties. The challenge lies in detecting these absorption features when they represent changes in stellar brightness of just a few parts per million. Advanced computational algorithms compare the observed spectrum of K2-18b with theoretical models containing thousands of possible molecular absorption lines. This comparison process must account for the complex ways that different atmospheric layers, temperatures, and pressures affect the strength and shape of absorption features. The resulting analysis provides not only identification of atmospheric components, but also estimates of their relative abundances and vertical distribution within the planet's atmosphere. The seasonal monitoring program for K2-18b has begun to reveal temporal variations in atmospheric composition that could provide crucial insights into the dynamics of the planet's atmospheric power system. While the planet's 33-day orbital period is too short for traditional seasonal variations, longer-term changes might result from atmospheric circulation patterns, geological activity, or potential biological cycles operating on different timescales. Detecting genuine temporal variations requires extremely precise measurements that can distinguish real atmospheric changes from instrumental drift or systematic effects. The James Webb Space Telescope's exceptional stability and precision make such measurements possible, though they require careful calibration and comparison with stable reference sources to ensure reliability. The implications of any confirmed temporal variations in K2-18b's atmosphere would be profound. Non-biological atmospheric processes typically produce either constant compositions or changes that follow predictable patterns based on orbital mechanics or stellar activity. Irregular or cyclical variations that cannot be explained by these physical processes might indicate biological activity, particularly if they involve gases like methane that are known to be produced by trials. Living organisms. The comparative analysis of K2-18b with other sub-Neptune planets has revealed both similarities and striking differences in atmospheric composition and structure. While most planets in this size class retain significant atmospheric envelopes, their specific chemical compositions vary widely depending on factors such as stellar irradiation, planetary mass, and formation history. This diversity suggests that K2-18b's particular atmospheric characteristics might be relatively unusual, even among similar planets. The database of sub-Neptune atmospheric observations continues to grow as more planets are studied with advanced spectroscopic techniques. Each new world adds to our understanding of the range of possible atmospheric compositions and the factors that determine planetary atmospheric evolution. This comparative approach helps scientists understand whether K2-18b represents a typical example of its planetary class, or an exceptional case with particularly favorable conditions for potential BAL. Life. The theoretical framework for understanding sub-Neptune planet formation and evolution has been significantly advanced by observations of worlds like K2-18b. These planets likely formed beyond the ice line in their stellar systems, where water could condense into solid ice grains that enhanced planetary accretion. Subsequently, many of these worlds migrated inward to their current positions closer to their host stars, undergoing significant atmospheric and thermal evolution during this migration process. The migration history of K2-18b has important implications for assessing its potential habitability. If the planet formed in the outer regions of its stellar system and then migrated inward, it might have initially possessed a very different atmospheric composition dominated by hydrogen and helium. The current atmospheric composition, rich in water vapor and other heavy molecules, might have developed only after the planet settled into its current orbit within the habitable zone. Understanding this evolutionary pathway helps scientists assess how long K2-18b might have maintained conditions suitable for life. If the planet's current atmospheric composition is a relatively recent development, any potential life forms might be evolutionarily young compared to Earth's ancient biosphere. Alternatively, if suitable conditions have persisted for billions of years, there might have been ample time for complex biological evolution to occur. The role of impact events in shaping K2-18b's atmospheric evolution represents another area of active research. Large impacts from asteroids or comets could have delivered substantial amounts of water and organic compounds to the planet, while also potentially stripping away portions of the atmosphere. The balance between atmospheric delivery and loss through impact processes could have significantly influenced the planet's long-term habitability. Computer simulations of K2-18b's atmospheric dynamics have revealed complex three-dimensional circulation patterns that redistribute heat, moisture, and chemical species throughout the Barents Sea. Planet's thick atmosphere. These circulation models suggest that the planet might experience powerful jet streams and convective systems that transport atmospheric constituents between different regions and altitude levels. The efficiency of atmospheric mixing has important implications for interpreting biosignature observations. If biological processes are occurring in localized regions of the planet, efficient atmospheric mixing would distribute the resulting gases globally, making them detectable in observations that sample the grid. Planet's disk averaged spectrum. Conversely, if mixing is inefficient, biological signatures might remain localized and could be more difficult to detect with current observational techniques. The potential for atmospheric stratification on K2-18b creates additional complexity in interpreting spectroscopic observations. Different chemical processes might dominate at different altitudes within the planet's atmosphere, creating layered chemical environments that could each contribute differently to the overall observed spectrum. Understanding this vertical structure is crucial for accurately interpreting atmospheric composition measurements. High-altitude atmospheric chemistry on K2-18b might be dominated by photochemical processes driven by stellar ultraviolet radiation, while deeper atmospheric layers could be more influenced by thermochemical equilibrium or potential biological processes. The transition between these different chemical regimes could create distinct atmospheric layers with very different compositions and properties. The study of atmospheric aerosols and cloud particles on K2-18b represents an emerging area of research that can provide additional insights into the planet's atmospheric processes. Clouds and hazes can significantly affect atmospheric chemistry by providing surfaces for heterogeneous chemical reactions and by influencing the planet's energy balance through their effects on radiative transfer. The composition and properties of cloud particles on K2-18b would likely be very different from those found in Earth's atmosphere. The planet's atmospheric pressure and temperature conditions, combined with its unique chemical environment, might lead to the formation of exotic cloud types composed of materials that rarely condense in Earth's dapple. Atmosphere. Detecting and characterizing cloud properties on K2-18b requires sophisticated analysis of how atmospheric particles scatter and absorb starlight at different wavelengths. These scattering effects create subtle changes in the observed spectrum that can reveal information about particle sizes, compositions, and vertical distribution within the atmosphere. The potential role of lightning and electrical phenomena in K2-18b's atmospheric chemistry has also attracted scientific attention. Lightning can drive chemical reactions that would not occur under normal atmospheric conditions, potentially producing or destroying trace gases that might be mistaken for biological signatures. The thick atmosphere and dynamic weather systems expected on K2-18b could support frequent electrical activity. Laboratory experiments simulating the atmospheric conditions expected on K2-18b have provided valuable insights into the chemical reactions that might occur in such environments. These experiments reveal how different gas mixtures react under high pressure and temperature conditions, helping scientists understand which chemical processes could naturally produce the observed atmospheric asker. Composition. The experimental work includes studies of how potential biosignature gases like methane might be produced through non-biological processes under the specific conditions expected on K2-18b. Understanding these alternative production mechanisms is crucial for assessing whether observed atmospheric compositions necessarily indicate biological activity. The development of new analytical techniques specifically designed for exoplanet atmospheric studies continues to advance the field's capabilities. Cross-correlation spectroscopy, for example, can detect trace atmospheric components by comparing observed spectra with high-resolution molecular templates, potentially revealing gases that are too weak to white tea. Detect through traditional methods. Bayesian atmospheric retrieval techniques have become increasingly sophisticated, allowing scientists to quantify uncertainties in atmospheric composition measurements and to explore the full range of atmospheric models that are consistent with the observational data. These advanced statistical methods help ensure that scientific conclusions are appropriately cautious and well supported by the available evidence. The integration of multiple observational techniques provides complementary information about K218b's atmospheric properties that strengthens overall scientific understanding. Transit spectroscopy reveals the chemical composition of the atmosphere, while secondary eclipse observations can provide information about atmospheric temperature structure and DEI night temperature variations. Phase curve observations, which monitor how the planet's thermal emission changes as it orbits its star, can reveal information about atmospheric dynamics and heat redistribution efficiency. These observations require extraordinary precision, but can provide unique insights into how efficiently the planet's thick atmosphere transports heat from the day side to the night side. The search for radio emissions from K218b represents another observational approach that could provide information about the planet's atmospheric and magnetic properties. Radio observations might detect emissions associated with atmospheric chemistry, auroral activity, or other electromagnetic phenomena that could reveal additional details about the planet's environment. The technological challenges involved in studying K218b have driven innovations in multiple areas of astronomical instrumentation and analysis. Ultra-stable spectrographs, advanced detector technologies, and sophisticated calibration procedures developed for exoplanet observations find applications in many other areas of astronomy and space science. The computational demands of analyzing K218b's atmospheric data have contributed to advances in high-performance computing and data analysis algorithms. The massive datasets generated by modern space telescopes require innovative approaches to data storage, processing, and analysis that benefit numerous other scientific fields. The international coordination required for K218b research has strengthened scientific collaborations and established frameworks for sharing observational data and analytical results. These collaborative networks facilitate rapid progress in understanding exoplanet atmospheres and help ensure that important discoveries are thoroughly vetted by the global scientific community. The training of early career scientists through K218b research has created a new generation of experts in exoplanet atmospheric analysis and astrobiology. Graduate students and postdoctoral researchers working on this project develop skills that are highly valuable for future exoplanet missions and related scientific endeavors. The public outreach efforts associated with K218b research have helped communicate the excitement and importance of exoplanet science to broad audiences. Planetarium shows, educational websites, and media coverage have introduced millions of people to concepts in atmospheric chemistry, astrobiology, and the search for life beyond Earth. The cultural impact of K218b research extends beyond immediate scientific and educational effects. Artists, writers, and filmmakers have drawn inspiration from the possibility of life on this distant world, creating works that explore themes of cosmic connection, environmental responsibility, humanity's place in the universe. The philosophical discussions stimulated by K218b research have engaged scholars from diverse disciplines in examining fundamental questions about the nature of life, consciousness, and our responsibilities toward other forms of life in the universe. These interdisciplinary dialogues help contextualize scientific discoveries within broader frameworks of human understanding and meaning. The economic impacts of K218b research include both direct expenditures on telescopes and observations and indirect benefits from technological innovations and workforce development. The high-technology skills developed through exoplanet research contribute to economic competitiveness and innovation in multiple sectors. The policy implications of potentially confirming life on K218b extend to areas such as space exploration priorities, international cooperation frameworks, and environmental protection strategies. Such a discovery could influence how societies allocate resources for scientific research and space exploration programs. The long-term vision for K2-18b research includes plans for even more detailed atmospheric characterization using next-generation telescopes and analytical techniques. Future observations might detect additional biosignature candidates, characterize atmospheric dynamics in greater detail, and potentially provide more definitive evidence for or against biological prees. Activity. The development of theoretical frameworks for understanding life in sub-Neptune environments continues to evolve as scientists grapple with the implications of potential biosignature detections on K2-18b. These frameworks must account for the possibility that life could emerge and thrive under conditions very different from those found on Earth. The comparative planetology approach to understanding K2-18b places this world in the context of planetary formation and evolution processes operating throughout the galaxy. By studying how planets of different sizes, compositions, and orbital characteristics develop their atmospheric properties, scientists can better understand the factors that determine habitability. The statistical analysis of exoplanet populations suggests that sub-Neptune planets like K2-18b are among the most common types of worlds in the galaxy. If such planets can indeed harbor life, the total number of potentially inhabited worlds could be far larger than previous estimates based on Earth, like planets in the habitable zones of Sun-like stars. The implications of this statistical perspective are profound, suggesting that life might be a common rather than rare phenomenon in the universe. This possibility encourages continued investment in exoplanet research and the search for biosignatures on worlds that might be very different from Earth but still capable of supporting biological pore. Processes. The timeline for future K2-18b observations depends on telescope scheduling, funding availability, and the development of new observational capabilities. The James Webb Space Telescope will continue to monitor this world periodically, building up a longer-term record of its atmospheric properties and any temporal variations that might occur. Ground-based telescopes are also contributing to K2-18b research through complementary observations at wavelengths and with techniques that are difficult to implement in space. The combination of space-based and ground-based observations provides a more complete picture of the planet's properties than either approach could achieve alone. The anticipation surrounding future K2-18b results reflects the profound significance that confirming life beyond Earth would have for human understanding of our place in the cosmos. Such a discovery would provide concrete evidence that the processes leading to life are not unique to Earth, but can operate under a wide range of planetary conditions. As we continue to push the boundaries of what is possible in astronomical observation and analysis, the study of K2-18b represents both a culmination of past achievements and a foundation for future, discoveries. The techniques and insights developed through investigating this remarkable world will guide the search for life throughout the galaxy for generations to come, bringing us ever closer to answering one of humanity's most profound and enduring questions about whether we are truly alone in the vast expanse of space and time that surrounds our small blue planet.